Thank you very much. Good morning, everyone. I'm Noelia Barrio, and on behalf of my quartz today, I would like to talk about functional multistage engageable structures for fin-rate soft robotic fingers, a research done in KTH Royal Institute of Technology. Taking it from the beginning, the fin-rate effect is a bio-inspired gripper that takes inspiration from fish fins. This is a basic structure that when we apply an external force, in nature's case, water current, deforms on the opposite direction of that force, therefore being a compliant structure. As you can see, the fin-rate finger is a triangular structure made out of a soft material with an outer wall and some inner ribs to deliver stiffness. Its main weaknesses, they're based from the fact that we're using a soft material, normally TPU, for printability reasons, that then will therefore experience molding effect, fatigue, hysteresis, and of course, time deterioration. Also, since we're using a passive structure, we rely on contract-driven deformation, and we don't really have an active control over our system. Therefore, precision is compromised, and also response times are slow. We'll be focusing on these two main aspects in our designs to enhance fin-rate grippers. With the will to develop grippers that will be good at handling brittle objects, my colleagues and I developed designs with multi-stage different phases with variable stiffness that will cause no damage to the object being gripped. On the left, we've got the conventional design. Right next to it, the adjoining ring design, characterized by two inner rings whose collision will deliver friction, therefore opposing deformation. We can then talk about two different phases, before and after the rings collide. We also developed a multi-inner ring design based on a similar principle. We've got three rings, one within each other, that will progressively be compressed, and once again opposing deformation. Then we can talk about three different phases, as each of the different rings are subjected to compression. In order to govern the triggering points of the different stages, we can manipulate the parameters h, distance between the different rings, d1 and d2. Through these pictures, screenshots of some simulations, we could get a better insight on the different phases. Starting out with the adjoining ring design, we can see a stage number 1 in which some deformation happened, but still the rings don't collide against each other. To the left, the triggering point when they start touching one another. And finally, after they start colliding and delivering friction, we get to still touch our fingers, having some more deformation on them, but now with a higher resistance to it. The multi-inner ring design follows similar principle. Stage number 1, just the outer ring is being subjected to compression. Then we've got our triggering point when the middle ring will also start to get compressed. To its left, the middle ring is already being compressed, and right next to it, the three rings are opposing resistance due to this compression stage. Talking a little bit more about simulations, me and my colleagues used a hyperelastic nonlinear model to simulate the behavior of TPU, and we also loaded our fingers on the area that we consider contact will take place. Therefore, you can see on the graphs how our designs were softer than the conventional fin-rate design, meaning they're more compliant and a better option for lower loading situations. You can also see how after the different triggering points take place, our structures get stiffer, meaning they will only be harder and harder to deform, therefore gaining control over the state of our fingers. Later, we 3D printed our designs using TPU95, and we subjected them to some testing involving dial indicators and also weights attached to the string. This way, validating our results. Just as the conventional fingering fingers, we've got a structure that's compliant to different convexity levels. Also, we believe that it's great at handling brittle objects without any risk of damaging them if a proper design according to parameters I mentioned before is done. Of course, it's also safe for human interaction, since we are, as we all do, talking about soft materials. Then we believe potential applications for our fingers would be food processing lines, pick and place, and output of hard steel. Also, of course, added to automatic sorting processes of brittle objects. We believe it is then safe to say that our fingers, through design, can adapt to different stiffness and convexity needs, so that now we can be able to grasp brittle objects without damaging them, as I said before. Furthermore, precision is enhanced since we get a better control over deformation. We also are able to compensate a little bit for the Mullins effect, the inherent softening of TPU, fatigue, hysteresis, and the degradation of the material, leading to higher repeatability and accuracy. Lastly, we also get faster response times, since we're able to snap back our fingers due to the involvement of our internal structures after the triggering points, and then we're able to subtly lower response. Thank you for your time. I'll be more than happy to answer your questions in the poster session.
Thank you.